Okay, so now it's time to do some math. And this is the hard part of this chapter, is trying to figure out which one of these equations do we want to use. But we do have basically 4 kinematics equations. And you know what? You had it right when you were in 6th grade and you learned distance equals rate times time, because that's still a valid equation. That still works for physics. See how smart you were? And this rate here, okay, it has to be in meters per second, because you're going to multiply it times seconds, and see how your seconds are going to cancel, and that's going to give you a distance in meters. Okay, so your rate's in meters per second, so that means it's some sort of speed. Okay, it's going to be used when you have a constant speed or when you know the average speed, or constant velocity. So if you knew that it was going at the same speed the whole time, then you can use distance equals rate times time. Or if you've somehow found the average of the speed, the average speed over its time, then you can do that. So, very good equation, still works even though you're a big kid now. The next equation is, okay, so a lot of people have trouble with the math of this one, but it's just x equals 1/2 at squared, and a being your acceleration, and then v initial t, so you're going to multiply by your initial velocity. You're going to multiply your initial velocity times your time, and then your x initial. So this is like your starting position, and this is your ending position. Now, most of the time, this is going to be 0. Your initial position is going to be 0. So your x over here is going to be your displacement. So this is going to be displacement. So make sure you get that straight. This is going to be displacement. I guess I'll write that in for you. Displacement. Okay, many times this is 0, a lot of times. So it's kind of implied that it's going to be starting, you kind of just start your number line at 0, 0, 0. Remember how when we were doing the videos, we moved the axis, so we started at 0, just to make our life easier. Those of you that are in calculus are going to learn that the next equation is the derivative of the first, but you don't need to know that. It's fine, because you're going to write all 4 of these equations on your handy dandy equation sheet. But you're going to take your acceleration, multiply by your time, and add your initial velocity. Here, in the one above it, it's only the time that gets squared. So it's acceleration and then square your time. And your calculator will do orders of operations. So you just put in 1/2, or you can put in 0.5, acceleration, and then whatever your time is, and then square that. And your calculator knows how to do that. So don't worry about orders of operations. Just make sure you don't square both of those. You just want to square the time. And then the last one is a handy one. This is a handy equation. This one's handy when you have no time. So if nobody tells you anything about a time, this is a handy equation. This one is when you have no distance. So it's often easier to choose your equation based on what you don't have. And then this one has no final velocity. Okay, so when we go to solve our problems, what we're going to do is we are going to list all of our kinematics variables, and then we're going to read the problem and see where each one fills in. All right, so here's a sample problem. Bobby's traveling at 5 meters per second and goes 4 kilometers. How long did she take to do that? Okay, so to start the problem, what we're going to do is we're just going to go v initial, v final. We're just going to list our variables, acceleration, time, and our displacement. Okay. So her initial velocity, okay, so see how this is meters per second. So Bobby's traveling at 5 meters per second. So since we see this meters per second, that's going to tell us it's a velocity. And she's traveling at 5 meters per second. Do we have any indication there that she's speeding up or slowing down? Now it kind of looks like her initial velocity is 5 meters per second. And her final velocity is also 5 meters per second. So what does that tell us? She's going at a constant speed. Ooh, there's a hint. Which equation can we use? But let's go ahead and do this. So if she's going at a constant speed, what is her acceleration? Are you speeding up or slowing down if you're going at a constant speed? No. So your acceleration is 0. Okay. And she goes 4 kilometers. What do we measure in kilometers? Yeah, that's going to be a distance. So we're going to go ahead and write 4 kilometers. Did you notice something, though? 4 kilometers. What do we have to do that? Okay, we need to make sure that our distance and our speed have the same distance unit. Okay, so our initial velocity here is in meters. So we need to take those kilometers down there and change them to meters. So this is going to be, you do it, you should be able to do this now, 4,000 meters. And then our question asks us, how long did it take? So that's the question. How long did it take? Okay, so think, if I asked you how long did it take you to do your homework, you would give me an answer in time, right? So we're looking for the time. We don't know that. So this is a constant speed situation. Which one of our kinematics equations can we use with constant speed? We had it right in 6th grade. Yay! Okay, so let's go ahead and write down our equation. Distance equals rate times time. Okay, so remember that rate is a speed. Okay, how fast were we going? We were going 5 meters per second, and we're looking for the time. So what do you think we're going to put in for D? How far did we go? What was our distance? That's the 4,000 meters. Okay? Oops. Let's not put the meters in there because that kind of confuses. It looks like another variable. So when I put things into the equations, I generally leave the units out of my equation just because I find that it kind of confuses the math. It's like, what's my variable? What am I looking for? So we're going to divide both sides by 5, divide by 5, and we get t equals, well, gee many, 800 seconds. I have no idea in the real world what 800 seconds is. So anytime you get some sort of number that you have no concept of, like 60 seconds, I have an idea of how long that is. 800 seconds, I have no idea how long that is. So what we're going to do is convert that to a reasonable time unit. Convert to a reasonable time unit. And a reasonable time unit is something that you recognize. So we know that 1 minute is 60 seconds. You should be able to do this without me. And 800 divided by 60 is 13.3 minutes. It's actually 13.33333. but we just leave it as 13.3. That is a time unit that we have an idea of. It took me a little bit over 13 minutes, or it took Bobby a little over 13 minutes to go 4 kilometers at 5 meters per second. Okay? All right, let's try a different one. Okay, so here we go. We're going to list our variables again. So we're going to go V initial, V final, acceleration, time, displacement. And we're going to read the problem. Okay, so I want you to notice how I read the problem. I don't read the problem like Marie started at rest at a stoplight when light turned green. She accelerated for 15 seconds at 3 meters per second. How far did she travel? Because that's how you read it. Okay, read it just one step at a time. Maria started at rest. How fast are we going when we're going at rest? Aren't we stopped? How fast are we going when we're stopped? Are we going 0 meters per second? Okay, so that's 0 meters per second. And she started at rest, so that tells us it's her initial velocity. When the light turned green, she accelerated for 15 seconds. 15 seconds. What do we measure in seconds? Notice I'm looking at the unit to see where I'm going to put it in my thing. You're right. Seconds is time. So we're going to go 15 seconds at 3 meters per second squared. What do we measure in meters per second squared? Good. That's your acceleration. Okay, and then the question says how far. So which one of these do we measure in is a distance? How far did I go? That's our x, right? So that's what we're looking for. We're looking for how far did she go. All right. So nobody said anything to us about the final velocity. Do you see that in the problem? And which equation's good when you have no final velocity? Do you see it's the second one? See? No final velocity. We're going to use the second equation. Okay, so we're going to write down our equation before we plug anything in. X equals 1/2 AT squared plus V initial t plus X initial. Okay, so my initial spot is 0 because we just want to know she went from here, so we can set 0 at her beginning spot. So let's plug everything in. We have X equals 1/2 her acceleration, so times 3, times her time, 15, and only the time is going to get squared, plus my initial velocity, which was 0. 0 times 15. What's 0 times 15? 0. So we don't have to do that. So see, we've got easy math. It's actually easy to solve. It looks ugly, but it's not. And when we do all that, we get, so we get X equals 337.5 meters. She went quite a distance. That's 3 football fields. Okay, the question now may ask, what was her final velocity? Okay, so this brings up an interesting thing because there are many roads to Rome. Okay, and we're going to do it both ways. All right, so we're going to get a clean page. Okay, we see that there are actually two of them that have final velocity in them. Do you see that? That has final velocity and that has final velocity. Well, guess what? Since we know all the rest of the variables, since we know everything else, whoops, that was interesting, then it doesn't matter which equation we use. Our initial velocity was 0. Our final velocity, we don't know. We know our acceleration was 3 meters per second squared. We know that our time was 15 seconds. And our distance, now we know that. We just solved for that. 337.5 meters. Okay. So if we go back and we look at our equation ways just to show that we get the same answer both ways. So we're going to write down our equations. V final is equal to acceleration times time plus V initial. That's the easier one to use. There's no squares or anything in it. So V final, that's what we're looking for, is equal to our acceleration, we said was 3, times our time, 15, plus 0. 0 is our initial velocity, so that goes away. And so we get a final velocity of 45 meters per second, which frankly is flying. Okay, I hope that stoplight was getting her onto the freeway. All right, let's try it the other way. Let's try it with the V final squared is equal to V initial squared plus 2AX. Okay? So we're looking for V final. That squared is equal to our initial velocity, which was 0, squared, which is still 0, plus 2 times our acceleration was 3, and our distance was 337.5 meters. Okay, so we're going to do all of this math here, and we're going to end up with V final squared equals, I don't know what all that comes out to, times 2 times 3 times 337. That's 2025. Well, that doesn't match 45. Oh, look, it's V final squared. So we need to take the square root of both sides. And when you take the square root of 2025, you get V final is 45 meters per second. So there are many roads to Rome. Don't think that just because you did it one way and your next door neighbor did it a different way that you're necessarily wrong, okay? There are many roads to Rome. So we have some implied information. You kind of saw it in the last problem that we did. When you are at rest, okay, your velocity is 0. It might be an initial, it might be a final. When you come to a stop, okay, your final velocity is 0 meters per second. When you drop something, the initial velocity is 0 meters per second. How about this? And we saw this in the first one when you're going at a constant speed. your acceleration is 0 meters per second squared. And that's going to come into play when we do forces too. So that's an important idea. Constant speed, your acceleration is 0. Constant speed, no acceleration. Okay. We will add some more implied information from the word problems when we do free fall, but this will get you started. So this information is implied. So it won't actually say, hey, your initial velocity is 0, your final velocity is 0. So you need to infer this from the problem. And so this is also good information to put on your handy dandy equation sheet. All right, let's get some practicing done. Good luck.